Friends, let us continue our discussion on kinetics of catalytic reactions, and in the last class we discussed about why catalysis is so important, or catalyst is rather so important, not just for enhancing the rate of reaction, but also for increasing the yields and selectivities, reducing the energy as well. So, let us now try to look at how we define the kinetics, or how we derive the kinetic expressions, rate expressions for catalytic reactions. Let me recap the number of steps that are essential for a catalysis reaction to occur, and we are talking mainly in terms of gas solid or liquid solid catalysis. So, you have a solid particle, let us say catalyst. So, this is my catalyst, and surrounding this are my reactants, let us say A1, A2 and so on. So, what must happen first is that the gas reactant molecule from the bulk phase. So, this is all my bulk phase, and this is the circle is my catalyst phase. So, what must happen is that the gaseous reactant molecule should come to the catalyst surface, and in order to simplify the analysis, we assume that all the resistance to mass transfer is located in a thin film which surrounds this catalyst surface. Okay. So, from bulk to the end to the edge of this thin film shown by this dotted line, there is no resistance. All the resistance to mass transfer is located in this thin film. Now, one important point that I mentioned last time also, that is when you have heterogeneous system, that is when you have more than one phase like gas and solid over here, there are boundaries between these two phases. So, there is a gas phase, there is a solid phase, and there is a boundary between the two phases. Moment we have boundaries, there is a resistance to transfer, and it is this resistance which actually influences at what rate the reaction will take place. That is, whether the reaction will be kinetically controlled, or the kinetics that plays a role, or it is mass transfer controlled, will be determined by what kind of resistances we encounter when there is a transfer across the boundary. So, to begin with, we say that the resistance is localized in this thin film over here, this is surrounding the catalyst surface. So, once the gaseous molecule reaches the surface of the catalyst, since the catalyst is porous, it has to diffuse inside, get adsorbed onto the active component, undergo chemical reaction, get desorbed from the surface of the catalyst, flow backward in this channel to the external boundary, from external boundary to this edge of this resistance boundary or film boundary, and from there back to the bulk phase. So, there were total 7 steps that we talked about. First and 7th step, external mass transfer. Number 2 and 6, internal mass transfer, that is external mass transfer relates to transfer across this boundary. Internal mass transfer relates to how the transfer is taking place in the pores, and then steps 3, 4 and 5 reaction steps, that is adsorption onto this adsorption onto this material, then surface reaction and then desorption. So, these are all 3 reaction steps. So, kinetically speaking, we are right now concerned with only this step. We will bring in this external and internal mass transfer maybe few sessions down the line, and how they influence the rate of reaction. So, when we talk about the kinetics, we are interested in finding out what is the rate of a reaction which is a result of these 3 steps: adsorption, desorption and surface reaction. That is what we call true kinetic rate. And if this rate is what is controlling. Now, what is idea of controlling? We have kinetic rate. Similarly, we will have external mass transfer rate, we will have internal mass transfer rate. So, depending upon which of these 3 processes is slow, that will determine the overall rate of this reaction. So, if the reaction rate is the slowest step, the reaction is the slowest step compared to the diffusion, then we say that this reaction is kinetically controlled. On the other hand, if the external mass transfer is the slowest, we say it is external mass transfer control. Similarly, internal mass transfer control, if internal mass transfer is one of the slowest step in the reaction. So, let us start looking at what happens when this adsorption, desorption, or how do we characterize these reactions. And to do that, let us start with a reaction. Let us say that we have a reaction A going to B. We can consider a reversible reaction, A going to B. So, now we will start our analysis by considering the first step, the adsorption step. So, the mechanism that we talked about can be represented in the following form. We have, now let me just say that this is my catalyst surface now, okay, and this is the location where the active material is there. Recall that we talked about the catalyst is not entirely made up of the material which will bring about this transformation, because if you are making a porous catalyst, at least you need something to hold this porous structure together, and many times that is not feasible with the catalytic material itself. And besides, if you are for example using a catalyst like platinum, having a platinum ball as a catalyst will be a disaster, because the cost of that catalyst itself will be more than any profit that you can probably make from making this product. So, what is done is you have a support material onto which this platinum is deposited. So, this is, let us say, one of those sites where the platinum is deposited. We will call this site as L. Okay. We will call this site as L, that is the ligand, and my A is going to interact with this active site L. So, my first step is A plus L gives rise to AL. I will call this AL as AL, A sitting onto the active site. So, this is, if you recall, my third step in the description or adsorption. Now, what happens when this catalyst acts? For variety of different reasons, and it is not in our scope to go into the mechanism, that is the chemical mechanism of this catalysis. You will require a full course on chemical kinetics or catalytic kinetics to understand that, but let just say that it undergoes a transformation. So, from here it becomes my product B, but still attached to this active site. So, let me write my surface reaction so called because it is occurring on the surface of the catalyst. So, AL becomes BL. But if this B is attached to this catalyst surface forever, that is once it is bound, it is there forever, then obviously we cannot have our product back into our bulk phase. So, what must happen next is the B is detached from the catalyst site or desorbed from the catalyst site and moves back into the bulk. So, this step we call desorption. We call this step as desorption, and we can write this as B plus L. And this is what is happening when the catalytic reaction is taking place. Notice here that we started with an free active site and then we ended up with free active site. That is, we have the active site back after A got converted to B, A got converted to B, so that the next molecule of A can come back, interact with this L and go through this cycle. So, regeneration of this active site or catalyst is crucial, and this is the reason why many definitions of early definitions of catalysis were put forward in the following manner. One of them said that catalyst is a material which does not appear on reactant and product side. So, if you look at this overall reaction, I do not have my catalyst actively participating in the reaction. So, we have A going to B as a general reaction. But another definition also said that it is a material which appears on both reactant side and product side. So, that means A plus L gives rise to B plus L. If you add up all these three reactions, we will end up with this. So, my catalyst appears on both sides of the reaction, the reactant side as well as product side, and hence various different definitions. But it is important to realize that the catalyst site that we are generating must be same as the catalyst site we started this cycle with. That is, there should not be any chemical change in the structure of this catalyst site. For example, to give you an example, suppose, and it does happen indeed for some catalytic reactions, suppose while this chemical transformation is taking place and desorption is taking place, if this catalyst site is coated with carbon, let us say, okay, coated with carbon, then we can no longer say that the catalyst site that is regenerated over here is same as the what we started out with. So, this will be the catalyst site which got regenerated will be something different than the catalyst site we started out with, in which case the second molecule of the gas molecule cannot come and effectively bind. Now, if all sites on this surface happen like this, then of course, we have lost the catalyst forever. But what is more common is, for example, there are various different sites. This is not one. So, these are all our L's, and everywhere A is trying to interact and so on. So, it is possible that some sites carbon is deposited, some sites carbon is not deposited. So, when the catalyst was in the initial stages of reaction, let us say that it was fresh, we had many catalytic sites, but in such scenarios at the end of these reactions we are not able to retrieve all those active sites, but some of them have been lost. So, we say that catalyst has lost its activity or is partially deactivated because of some chemical transformations or other things, temperature for example may also play a role. So, because of that the catalyst has activity has decayed or catalyst has deactivated, does not mean that it has lost its activity fully. But to put hypothetical number, if 100 was the activity of the fresh catalyst, over a period of time we may end up the only 50% of those catalysts being active. Now, one of the motivations for using catalyst is to keep on using it, because if you see, if all these 100 were indeed regenerated, then we could indefinitely use this catalyst, and that is one of the motivations for using catalyst. But if only 50 are remaining after some time, then you may have to think of replacing the catalyst, that is throw away this old catalyst and start with the fresh catalyst, and periodically keep on refreshing your catalyst stock, replenishing the catalyst stock. So, that also becomes a crucial step in deciding on a catalytic reactor design. That is, how long are we going to use this catalyst, what is a good time to replace, because on one hand replacing the catalyst involves cost, on the other hand not replacing the catalyst means loss of activity and therefore lower productivity, lower yields and so on. So, one has to then strike a balance between the cost of the catalyst and loss in productivity and decide upon when to replace that catalyst. But now let us go back to our kinetics, and we will start with this adsorption reaction and write it simply A plus L going to AL. Now, you would have noticed, even though my last step is BL going to B plus L, this is actually nothing but reverse of my adsorption process of BL. So, whatever discussion we can apply to the adsorption step, the same discussion in the reverse manner applies to desorption. So, we will not be discussing desorption step separately, but it is understood that one is the converse or reverse of other. So, we let us now start writing the kinetic rate expressions. So, let us say that our attachment rate, that is adsorption rate, A adsorbing onto L, is a law of mass action kinetics. So, let us say it is some kinetic rate constant K A, concentration of my reactant A, and it will also depend on the concentration of the active sites Cl. Okay. So, that is a adsorption rate. I can similarly write the rate of AL going to A plus L, that is desorption, as Kd, D denoting desorption, A denoting adsorption over here, into CAL. Okay. So, I am right now focusing only on single step adsorption. I have not even brought in desorption, I have not even brought in surface reaction and then couple it with desorption. But let us look at what happens when we have adsorption and how do we develop adsorption isotherms. So, this is my rate of adsorption, this is my rate of desorption, and what happens at equilibrium. So, I will consider adsorption as an equilibrium process, at equilibrium R A, that is the rate at which A is adsorbing onto L and the rate at which AL is desorbing must be same, or in other words RA must be equal to RD. Okay. So, this is at equilibrium. Some of you may be wondering that we are trying to define the kinetic of a reaction and we already got equilibrium. Where did the kinetics go? But believe me, we will come to the kinetics very shortly. So, equilibrium RA must be equal to RD. What does this imply? This implies that Ka into Ca into Cl is Kd into Cal from definition of our adsorption and desorption rate. Now, what is it that we are trying to determine here? We are trying to find out that given concentration of A, Ca, what is the fraction of A that is at equilibrium with the catalyst. So, that means what is the concentration Cal. Now, if you look at this balance, we have one relationship. We will say that Ca is the concentration which is present in the system. So, we know that. So, this is an input, this is an output, and we have a relationship between input and output in which Ka, Kd are adsorption desorption rate constants, but there is another quantity Cal which we do not know. Knowing Cal would require that if suppose let us say this is my catalyst and these are all my active sites, and when the A is there, some of them have A sitting on it. So, on my catalyst surface, what do I have? I have vacant site L on which no A is sitting and an occupied site Al on which the reactant molecule has split. What I am interested in Cal is this concentration. So, what are the difficulties in knowing that? Difficulties are, to know this, first we have to know what is the total number of sites here, 5 as illustrated, 6 as illustrated in this example. It is just an illustration, but how do I know that a priori? It is very difficult, we do not know really, and on top of it we also do not know how many are occupied, because that is what we are trying to find out. So, what do we do with these vacant sites? And this is what we do with the calculation of vacant site, and this is an important concept which is commonly used. So, let me go back to my catalyst and let us say that these are some active sites, okay. Some active sites, some of them have been occupied by A, okay, and some are free as we talked about. But we also realize by looking at this cartoon that whatever it is, whether it is occupied red or unoccupied blue, the total number of sites on the catalyst are same. That is, in one scenario am trying to replicate the same active site. In one scenario, there may be 4 A molecules occupying 4 sites. In another scenario, there may be only 2 occupying. That may vary, that will vary depending on what is the concentration of A in the bulk, but whatever it is, the concentration or the total sites are same. So, if I say that my total sites on the catalyst is CT, then this must be same as Cl, the blue ones, plus Cal, occupied and unoccupied, but this number is constant. That's wonderful, because if this also now is a constant, then we can say that Ct must be, we can put for Cl, for example, Cl, we can use this relationship, or other way. Okay, let's use that relationship, namely Kd by Ka, Cal by Ca, okay, Kd by Ka Caa plus Cal is my Ct. So, now if we in this expression, all I need to do is to rearrange this equation, and if I do that, I end up with the following relationship. That is, if I rearrange this, I end up with Cal equal to Ka, I will talk about what is Ka, Ct Ca divided by 1 plus Ka Ca. What is my Ka? Ka, K capital A, is nothing but the rate constant Ka divided by the rate constant Kd. So, Ka is actually nothing but an equilibrium constant. Ka is nothing but a equilibrium constant, ratio of the adsorption rate constant to a desorption rate constant, and that you can see from here itself. Ka by Kd will be Cal by Ca into Cl, and that is nothing but our equilibrium constant. So, that is that Ka. So, now we know my fraction, or rather the total sites which are adsorbed are Cal equal to Ka Ct Ca by 1 plus Ka Ca, or I can also express the same relationship as the fractional coverage Cal by Ct, which we call as theta A, the fraction of this surface which is occupied by this catalyst. It is, for example, 2 by 8 in this cartoon in the first case, it is 4 by 8 in the second case. So, 50%, here it is only 25% and so on. So, this is nothing but Ka Ca by 1 plus Ka Ca, and that is my adsorption isotherm. You probably also will know it as Langmuir adsorption isotherm. What is a characteristic of this isotherm? The characteristic of this isotherm is, if I plot Ca versus theta A, it will be an hyperbolic curve like this. That is, when Ca is small, concentrations are small, the number of occupied sites will be also small. So, this is a situation where Ca is small. We go on increasing Ca, more and more A molecules will occupy. So, this is that intermediate step. So, let me say that this is a scenario at step 1. So, this is my step 1, this will be something at step 2. So, this is my 2, but then what happens if I keep on increasing the concentration of A. So, let us consider a third case, that these are my same active sites and I am increasing my concentration of A. So, more and more A are available. There will come a time when all the sites are occupied by A. All the sites are occupied by A. So, this will be my situation 3, which is what is happening over here. So, once all the sites are occupied, even if you increase the concentration of A, no more active sites available on the catalyst and therefore, the coverage cannot increase, or in other words, this fractional coverage if you are looking at will reach a value, theta will reach a value 1. So, let me recap this adsorption step. What we said was, we have A binding to L, step number 1, this is my overall reaction, this is my adsorption desorption rates. I assume equilibrium, then I say that total sites are either free or occupied, and do some algebraic manipulation to get my final adsorption isotherm. Okay. So, these are the steps that we follow for any adsorption isotherm. Important thing to remember, that when we say that the total number of sites is constant, we are considering a case when this catalytic cycle is going on, there is no deactivation. So, there is no loss of catalyst, because if suppose these are deactivated as shown in the violet color over here, if they are deactivated, then our CT is not constant. So, the key assumption here is that the total number of active sites are constant. That means, when the catalytic cycle is completed of adsorption, surface reaction, desorption, the vacant site we regenerate is same as the fresh site. If there is any difference, we have lost the catalyst. Okay. So, now let us quickly look at what happens other situations. This is the simplest situation, but remember that we have. So, let me erase all this, or let us start afresh by saying that we just now considered A plus L, or we considered A plus L goes to AL, and we saw that we get fractional coverage theta A as CAL by CT as Ka Ca by 1 plus Ka Ca. Okay. But in our gaseous reactant we have product B also. So, we could have B plus L giving rise to BL. So, both these things happening simultaneously. So, if you once again go through the same exercise. So, what we are essentially saying is these are the catalyst active sites, and some of which are occupied by A, some are occupied by B. So, what do you expect will happen? Now, there is a competition for this active site between A and B, which means that the adsorption coverage of A will now be lower. That is, if B was not there, we would have got certain coverage, because there was no competition. A binding to the active site. Moment B is present, there is a competition from B. So, the available sites for A now has gone down. So, if we if we carry out the same analysis by saying that same adsorption desorption rates of first reaction are same, second reaction are same, and using that equilibrium, and now we will have to of course use Ct equal to Ca L plus Cbl plus Cl. So, if you do all that, we will get for the second case theta A equal to Ka Ca by 1 plus Ka Ca plus Kb Cb, and similarly theta B will be Kb Cb divided by 1 plus Kb Cb 1 plus Ka Ca plus Kb Cb. Look at what has happened here. That is, let us compare this expression theta A with this when B was present. What does competition do? Competition has reduced the coverage of theta A, because we have additional term in the denominator. So, for competition has reduced the coverage of A. What else has competition done? We can also argue in the following manner: which one of the two will be more? Will B be adsorbed more or A be adsorbed more? What will it depend on? Obviously, it will depend on the concentration of A and B. That is, if concentration of A is more than that of B, you expect coverage of A will be more than that of B, no surprise there. But it also depends on the relative values of Ka and Kb. What is Ka? Ka is the adsorption constant for A. What is Kb? Kb is the adsorption constant for B. So, whosoever has higher value wins. For example, if Ka value is greater than Kb, then you can expect higher coverage of A compared to B. In fact, why you can expect? If concentrations of A and B are same and Ka is greater than Kb, then we can easily see theta A has to be greater than theta B. What does adsorption constant high value means? That means the affinity of A for the catalytic site is much higher than the affinity of B. So, A adsorbs more compared to B. Let us consider few other scenarios. Now, as I said, many of these reactions are gaseous, and many of the gases involved in these catalytic reactions are diatomic gases like H2, like O2 and so on. Now, there are two possibilities when these gases adsorbed onto the active site. So, let us say that we have, okay, let us put it over here, we have these active sites. One possibility is that this oxygen simply adsorbs as an oxygen molecule. So, molecular adsorption. Okay. So, if I call molecule of AO2 as A, then this is same as A plus L giving rise to Al. So, entire discussion that we had earlier applies equally well, but quite often oxygen or diatomic molecule undergoes dissociation and the adsorption is now as a atomic oxygen on two sides, okay, as an atomic adsorption on two sides. Okay. So, what happens in this particular case, and let me for sake of clarity, let us call this gas as A2, okay, not as species A1, A2, A3, but just atom A twice diatomic A2. So, if I say this is A2, then I need two active sites to give 2 Al, okay, for this case atomic adsorption. Okay. So, let me rewrite this. I think I should have written it separately. So, for the molecular adsorption, my A2 plus L A2L, only single site. For atomic adsorption, A2 plus 2L 2Al. A is my oxygen atom. Okay. I mean, it can be nitrogen, it can be hydrogen, or it can be even other diatomic gases. So, now here you will get same as before, theta A, that is my fractional adsorption. It will be for theta 2 A2L here will be Ka Ca by 1 plus Ka Ca. But if you go through the exercise for atomic adsorption, the same thing that we talked about, then we will get theta Al as root Ka Ca by 1 plus square root Ka Ca. I leave it to you as an exercise, where did this half came from or square root came from. If you know, this reaction will be Ka Ca2 concentration of A Ca into Cl square equal to Kd into Cal square. So, if you do that exercise, you will get this rate expression. So, here Ka Ca root Ka Ca. Okay. So, this is as far as the adsorption is concerned. This is the simplest kind of adsorption isotherm. Now, there are other types. In the Langmuir adsorption isotherm, we assumed that if these are my active sites, Langmuir adsorption isotherm is that all these sites are same energetically active, they are identical, there is no way to distinguish between the two. Okay. Now, another approach is to say that not all sites are same. So, I am going to just put some different symbol, I mean it differs, and in fact many times it depends upon their energetically different. So, it depends on how many are occupied. So, this may be the case when there are only few occupied, this may become the case when more are occupied. Okay. So, that means the nature of this active site depends on the fractional coverage itself. Okay. So, if one looks at such approach, we end up with theta A as this is what is called as Temkin isotherm. That is, these are energetically non-uniform. Okay. So, this is as far as adsorption is concerned. In fact, we can also get what we call Freundlich adsorption isotherm under these assumptions, where N and K are constants. So, we get Freundlich isotherm or Temkin. This is in fact Temkin isotherm is used in ammonia synthesis reaction. Freundlich isotherm is quite widely used, but most common is of course Langmuir adsorption isotherm approach, and this is what we will be carrying forward in our next session, where we now bring in surface reactions and see how these two interact to give us the kinetics of the process. So, that will be the topic of discussion in our next session. Thank you.